Welcome to Spring LIB.
Okay. The molar mass of your C6H12O2 is 116, and we know that we're instead getting a base peak of 74, which tells us that there's some sort of fragmentation going on. But in particular, in this problem statement, we've been told that this fragmentation includes a rearrangement, right? And so we're talking then about the most common form of rearrangement is the so-called McLafferty rearrangement. And so we're kind of saying, for which of these molecules is the McLafferty rearrangement going to give us a base peak of 74? Now recall that the McLafferty rearrangement is when we lose, like if we have, say, a 4-carbon chain. We need at least a 4-carbon chain for the McLafferty rearrangement to happen. And it basically has to do with chopping off that much of the molecule, right? And so everything on the left stays together and everything on the right goes off on its own. And we end up with something like this, and then the right-hand side forms a double bond. But basically, the idea is that in the McLafferty rearrangement, we'll retain the carbon that the carbonyl carbon will retain the carbon next to it, but then lose everything else down the chain except for the hydrogen that is on the alpha, beta, gamma carbon. Right? So we gain a hydrogen from the gamma carbon, but lose everything from the beta carbon on. And note that this requires that we have a molecule with a gamma carbon, for which, if we look at the molecules here, or our options, we've got 1, we've got 2, we've got 3, and we've got 4. Right? 1, 2, 3, 4. Well, Roman numerals 4, right? So 1, alpha, beta, gamma could be 1. For 2, all we've got is alpha and beta. It can't be 2. There's not enough carbons in the chain to do a McLafferty rearrangement. We cannot do it on the ester side, so it's not going to happen there. In terms of 3, all we have is an alpha carbon. But in 4, we do have alpha, beta, and gamma. So 3 is not an option, but it is possible for it to be 1 or 4. What I would argue is that it has to be 1, and that's because if we look at the math here, upon going from 116 to 74, right, we would have lost some 42 molecular weights worth of carbon, right? And so if it were, in fact, 4, right, we'd be cutting the chain basically at beta and gamma. If it's 1, we'd be cutting off beta, gamma, and the next carbon, right? So 3 carbons would be lost here. 2 carbons would be lost here. 2 carbons is going to be, a molecular mass of 24 plus a few hydrogens. Specifically, it'll have 2 less hydrogens, so it'll be 1 hydrogen because 1 goes over. Sorry, no, it'll be 2 hydrogens here and 2 hydrogens here. So that would have a total mass. We'd lose 28, right? And we need to lose 42 during the arrangement, right? So we need to lose an additional carbon. So it is, in fact, 1, right? Because what we'd be losing is hydrogens there, a hydrogen here. One of the hydrogens here actually ends up going to that oxygen, and then the 3 hydrogens here. Okay, but ultimately that makes 1, 2, 3 carbons is 36, and 1, 2, 3, 4, 5, 6 hydrogens makes 42. So it's only by losing or fragmenting between the alpha and beta carbon that we can lose the 42 mass units that we have to lose to go from the molecular ion to the base peak. Okay, and then I can show what that would look like in case you're curious. I mean, the answer is definitely 1, but what does this look like? The actual rearrangement. Okay, so you want to draw your carbonyl. I'll draw the ester side, doesn't really matter. The important thing here is that you draw this in a specific orientation. You want the first bond down to the left, up and to the left, and then up. Okay, and then as it happens, we have a 4-carbon chain, so I'm going to show that going up and to the left. And then I'm going to draw a hydrogen on that carbon. There is another one, but I'm going to draw one of them going up and to the right. And I will denote these again. This is alpha, beta, and gamma. Okay, and then recall that at this point in the process, before the rearrangement, what we would be dealing with here is an oxygen which has been turned into a cationic radical. Right, it would have lost one of its electrons during electron impact fragmentation. And so what's going to happen is that this hydrogen from the gamma carbon, along with 1 electron from this double bond, are going to form a bond. So that's going to form a new oxygen hydrogen bond. 1 electron, the other electron from this double bond, is going to start to form a double bond. Let me draw that a little better. Let's start a double bond here, combining with 1 electron from this carbon-carbon bond from the alpha-beta bond. Okay, the other electron from the alpha-beta bond is going to form a double bond between beta and gamma, and then the other electron from the gamma carbon hydrogen bond will form the other bond that forms a double bond here, with the net result then being, and let me highlight this hydrogen in red just so I can see. The net result here will be that basically everything on the left is cut off. Right, we're just breaking that bond. Okay, so we're going to end up with a double bond with that methyl group sticking off. We'll still have the 1 hydrogen here. We'll still have 2 hydrogens here that were always there. Right, there was 2 hydrogens there. Okay, and then over here, we'll now have a double bond there, a single bond to oxygen. The oxygen will still have a lone pair. It'll now have a bond to hydrogen, and then a single radical electron because nothing happened to that, so it'll have a positive charge. Okay, and so this, if you add it all up, we'll have a mass of 74. And this, the other piece of the rearrangement, will have a mass of 42. Right? Carbon, 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 that makes 36. Hydrogen, 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 3 more up here makes 42. And you can add this up as well. It'll give you 72. It's 16 plus 16 for each of the oxygens makes 32. 1, 2, 3 carbons makes 36. 1, 2, 3, 4, 5, 6 hydrogens, 74.